This is part 2 of the course that we're doing, which started with the evolutionary journey of the soul. And in this part 2, we deal with the multi-dimensional universe. As I said in part 1 of this course, we dealt with the evolutionary journey of the soul in the context of the dimensional structure of the universe. This part 2 will expand further on this. Our bodies are connected to the universal energy fields of light and sound. There are different forms of light and sound, and they work together in harmonic bandwidths and have a particular relationship with each other. We will be exploring some of these in the multi-dimensional nature of the universe. Their frequencies, that is, the frequencies of light and sound, determine their harmonic, sound, which is resonance, and color spectrum. And it also describes the relationship to each other, and the various harmonics create dimensionality. For instance, in our case, we experience our reality in harmonic bandwidth 1. Harmonic bandwidth includes 12 frequencies of light and sound that form a harmonic, just like in music. These 12 harmonic frequencies form the basis of density of reality, a hologram. Each cycle has 4 reality fields, harmonic bandwidths, so to pass through, also called densities or harmonic universes. Our conscious soul bodies must travel all 12 dimensions of these 4 harmonic bandwidths to return to source. And we're in a constant cycle of going through that journey. Here's another representation of this. You get dimensions 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And this forms a cosmic Cathara grid. So what is multidimensionalism? In the normal sense, it is the measurement of a space, say a room, its height, length and breadth, that gives you the dimensions or size of the room. In the universe, it is the measurement of both time and space, through the measurement of light and sound waves, their frequency, amplitude and intensity. To understand this better, we will use an analogy of a map of the universe, of the light and sound wave fields. What we generally think of when we think about the universe are all the stars and their solar systems, galaxies, and manifestations of light that we call the universe. As I explained in the Mastering the Hologram course, we create our own hologram of reality. So the sun, stars, planets, and galaxies are part of that hologram. They are manifestations of our soul body's energy fields and the universal template on which reality fields holograms are formed. It is important to understand that holograms are just reality fields in a particular density whose matter base is either physical matter, semi-etheric, etheric, or liquid light. Holograms are just fields of experiential reality divinely designed to assist souls in their soul evolutionary journey. The purpose of soul beings is therefore to provide for themselves experiences to test and refine their soul consciousness, in order to accrete, accumulate, and activate their soul codes to prepare them for the next part of their journey. Remember, we said in the last part of this course that we have 2 types of DNA. We have genetic DNA and junk DNA. Our soul codes correspond with our DNA. Our genetic DNA carries our genealogical history, and our junk DNA carries our incarnational history. And these are just forms of information. Our genetic DNA has been tampered with and distorted by the fallen ones by DNA manipulation that goes a long way back in our history. We no longer carry the universal blueprint of 3 strands of DNA in our physical bodies, but they still exist in our soul bodies. That is why soul living is so important, because we can accrete, accumulate and activate more of our DNA in phantom form and prepare our bodies for the transformation that will occur with ascension. In my travels with Aesmir through the universe, I became aware that the universe out there is actually the universe in there, and in fact that is what Aesmir was at pains to explain to me. He told me about the fractal nature of the universe and said if you don't get this, that the universe is a holistic system, you won't understand anything, and I'll deal with this more in detail later. The whole notion of God being out there, as expressed here, was promulgated by a variety of beings who have been the rulers of this particular part of our solar system and beyond, who have kept us blind and given us a belief system that God is out there. This reversed all our concepts and precepts of who we are and what God is, and was designed to keep us separated from each other and from creation and Creator. Knowing oneself as an individuated expression of the one thing changes all perceptions of life and reality here. Let's look more closely at the multidimensional structure of the universe. Each harmonic bandwidth has 3 dimensions. Harmonic bandwidths are also called densities and sometimes harmonic universes here. The 3 dimensions are sound, light, and pulse, or rhythm. The dimension of sound manifests in our hologram as magnetic energy and in our anatomies as female. The dimension of light manifests in our hologram as electric energy and in anatomies as male. The dimension of pulse manifests in our hologram as time and in our anatomies as breath. These are the properties that sound, light, and pulse manifest as. Sound, magnetic energy, female; light, electric energy, male; pulse, time, and breath. In each density there are 3 dimensions, and there are 4 densities of manifest reality in each universe, which adds up to 12 dimensions in each universe. So it could be illustrated like this. Dimensions 1 to 3 are density 1. Dimensions 4 to 6 are density 2. Dimensions 7 to 9 are density 3. Dimensions 10 to 12 are density 4. So in our soul evolutionary journey, we go through all these densities, and we go up until the 4th density, and then we come back again. But because we've accumulated certain soul codes in our soul bodies, the manifest form we take might be different. So we go through that process again and again and again. Collect soul codes, and then go back into manifest reality in density 1, and go through to density 2, to density 3, to density 4, collecting soul codes, and the more soul codes we get, our manifest form changes, so we have different experience of reality. And so we repeat the cycle over and over again until we've repeated it enough to become human form. So human form is now, we're in density 1. And what we've been trying to do in our evolutionary soul journey is to progress through to density 4 to 6, sometimes called D5 here. And the reason we haven't been able to do it because we've been phase locked, kept trapped and recycled here as soul beings. And the fallen ones have been using a technology called blank slate technology so that each time we incarnate here, our memories are wiped and we don't remember who and what we are. But we can change that, and we are going to change that. In each density, matter manifests in density of matter like this. Density 1 is dense physicality, where things are solid or appear solid. In density 2, matter is semi-etheric. In density 3, we have etheric matter. In density 4, we have liquid light or pre-matter. So pre-matter then goes back to physicality, it cycles around, goes up into the dimensions, goes to liquid light, pre-matter, goes back into the densities, and cycles around in this way until we have accumulated and activated enough soul codes to give us a different manifest experience in density 1. Above 12 dimensions, there are 3 more dimensions that connect 4 universes together, and they are called the God worlds or echo fields, resulting in 15 dimensions in total. The trick to learn is that this is a universal pattern, and it is fractal in nature. So what is a fractal? The term fractal is derived from the word fraction, which means a part of. This is somewhat better illustrated through fractal geometry, invented by French mathematician Benoit Mandelbrot. He noticed that there were many repeating patterns in nature, although the scale size of the pattern were not always the same. The patterns seem to be repeating themselves at various levels. These patterns repeat themselves geometrically throughout the universe, giving rise to the term as above, so below. If you aren't mathematically inclined, don't worry. You don't have to understand the mathematics, but rather the underlying principles that create this geometry. For those mathematically inclined, here's a video explanation.
Maybe this is Mandelbrot set back to basics. I need your help though. Can you think of a number?
7.
Good. Can you square that number?
49.
Can you do this while filming? You've done it correctly so far. Okay, next question, you're going to get upset. Square 49?
No.
Okay, good answer. The thing is, I don't really care about the answer. What I'm caring about is an iteration. I can keep asking you to do the same thing again and again. And if I asked you to pick a number and keep squaring it, you already know what's going to happen, right? It's going to get big.
It's going to blow up.
Is it? Square 1?
Okay, except 1.
Okay, good. Now square a half.
Okay, it's going to get smaller.
No. So sometimes it blows up, and actually that happens when it's bigger than 1, and it becomes quite obvious when you try it. But 1 doesn't blow up, so 1's different, and numbers less than 1, like a half, actually become a quarter when you square them, and that becomes a 16th, and so on. But then numbers much less than 1, like minus 6, and that one's blown up as well. So what I'm really talking about, and what iteration is quite often talking about, is when iterations are stable, when they sort of head towards somewhere you can see, and when they're not. And it's best to see this on a diagram. So have a look at my screen here. You picked the number 7, which is kind of off my screen here, but these red arrows, I'm moving them around. This is not the greatest diagram, let me get this clear to start with. It's just a line, but the arrows are heading that way, because when I square this number I'm moving around, they go that way, and they never come back, much like your 7 did. But if I go less than this number 1, they don't go that way anymore, they go that way. In fact, they head towards 0 and they're stable there. So for the sake of moving it around, it's kind of nice to see the difference. It's a really sharp line and it completely changes behavior, but that way they're unstable, that way they're stable. Stable, unstable, stable, unstable, stable, unstable. You get the idea. In fact, if you go negative, they're still stable. They head positive, because when you square a number that's negative, they get positive. Still head towards 0 until you hit -1, and then unstable. Stable, stable, unstable, stable. Now, despite all my commentary, it's not that exciting yet. And if you know anything about the theory of iterations and the consequences of them, or if you've watched any other video about the Mandelbrot set, you know that we're not just talking about real numbers, i.e. the numbers on the line I've just been showing you. We're talking about numbers in 2 dimensions, so complex numbers. And I'm not going to give you an introduction to complex numbers here, because I don't think you need to hear it. And there are other places you can get them. Holly on the Numberphile channel has done excellent videos about how this happens. But I want to show you the same comments that she's made on brown paper. I'd like to show you moving. Here's my 2-dimensional number line. Here is the number that you get to pick randomly. We can still do it in 1 dimension just by sliding along here. And the other dot that's moving around, this tiny one, is the square of the other dot. So 1 squared is about 1, bigger than 1 it heads off that way, lower than 1 it goes that way, but I can move off the line now. And it has a weirdly circular flavour to it, which I kind of like. It's like chasing the number around. It moves quicker than you expect, and that's already quite pleasing if you're a nerd like me. But what I'm really interested in is the iteration. If you keep doing the instruction, square it, square it, square it, we saw what happened on the real line. In 2 dimensions, it looks different. So it looks like this. So this line indicates if you start there, it goes to there when you square it, and then to there and to there. And so if I move this around, the picture is kind of pleasing, kind of wobbles around, but it's always heading towards the center, which I'll say is stable. And there's a reason there's a circle on the screen, because anytime I'm inside this circle, it looks like it's stable, even if it's kind of pretty as it moves. But if I go near the edge of the circle, it's less obviously stable. It takes a lot longer to get to the center, and if I go outside the circle, unstable. Stable, unstable, stable, stable, unstable, stable. This is a really nice demonstration of why complex numbers are helpful. Instead of your entire image of what's happening being on a line, you've got a picture, but it gets better, right? Instead of just squaring it, what would happen if you did square it, add something, square it, add something, square it? Now we could go back to the real line and see it happening on different dimensions, but I feel like I should just go straight into 2 dimensions. This is just the square, square it, square it, square it. This letter C is indicating a number I could add every time. So let me just slide it away from 0. At the moment it's not adding anything, but if I add this number, this red number, which is a complex number, 2-dimensional, you see something very different can happen. If I start with this number and I keep squaring it and adding that number, square it, add that number, square it, add that number, square it, add that number, this is the path it goes. And it makes a lovely star shape. What's interesting though is not just the star shape, although I kind of like it, is the stability. So all around here it's stable, and it always gives you the same sort of stability, like the starry stability, even if it's expanding or shrinking. I kind of get the feeling that sometime it's going to blow up, and it's not obvious where, because if I go near the circle, you think, it's going to blow up, it's going to blow, but it doesn't.
Oh, it's like... Oh, no.
So there was a moment there, so outside the circle, still stable, but somewhere else outside the circle, unstable. And in fact, it's not obvious where this is happening. Stable, unstable, stable, stable, unstable, no, stable, stable. But over here, inside the circle, always stable, unless I go there. I keep saying the circle as if it's important. It's really not important anymore. The boundary is clearly not a circle. But it's kind of nice to move this around and think that some places are unstable and some are stable. What I'd really like to see, and I hope you would too, is the boundary of stability. So let's see that. In fact, let's look at the boundary. If the number I choose to add each time is 0, you get the circle. And that's like the simple iteration. But if you choose to add something different, by the way, I'm gonna write something down here. What I'm capturing is this iteration, which always looks a bit technical. And if I cover that bit up, it's what we did at the beginning. I said, square a number, and that's your new number. Square it, square it, square it. But instead of just squaring it, you do square it, add something. They use C for it's a constant, but it's a complex number. Now we're ready to look at that. If C is 0, you get a circle. If it's not 0, this is where my brain melts a little tiny bit. If C is not 0, the shapes become these shapes. And I always find this a little bit of a shock. There may be some familiar looking shapes, I don't know. But sometimes they're not even connected together. They're like dusty little particles. And these regions, particularly when there's obviously a region, which is not a circle necessarily, they're called Julia sets. And again, Holly's done a really lovely video about Julia sets. There's a bit of history about Julia sets found by Gaston Julia, hence the name, who was a guy, a French mathematician, I think, early 20th century. He did it without a computer. Like, he wasn't able to just do this and move on GeoGebra and see the boundary. He was doing this by hand and realising there was some beautiful structure. Like, I mean, every time I tell the story, I'm like, fair play. He also is really interesting in that he had no nose. Genuinely, you go and find a picture of Gaston Julia, he has a leather thing across his face. His nose was damaged in, I think, the First World War. Before I leave Julia entirely, the sets that you can see give you a little bit of a hint about what's coming. So let me show you two things about the Julia sets. First of all, the simplest one is a circle. It's not that exciting, but they are exciting, but they're not always obvious regions. Sometimes they look like they're separate regions. These don't look like they're connected. The way I'm animating it here, they're all slightly dusty looking. That's just the way I'm making it happen quickly. But sometimes they're definitely not joined together. And sometimes they look like things you might recognize. The outline is looking vaguely like something I've hinted about this video maybe looking like. But there is something important that Holly mentions in some of her videos about which ones are joined together, connected mathematically, and which ones are disconnected, separate like dust. Let me show you what they end up describing. So if we go back to this diagram when I did the iteration, we were originally starting by you picking a number and squaring it. What happened in 1979 is a guy called Benoit, that was his first name. It didn't get better for him, his surname was Mandelbrot. He's a very famous figure in mathematics these days, but it was 1979, 1980. It's kind of recent in the grand scale of mathematics. Benoit was like, I wonder what happens if I always start at 0. Instead of me saying pick a number, I would say like, pick a number as long as it's 0. And then all I really care about is what's the constant I add each time, and which ones of those give me stable, and which ones don't. Now, he didn't have a good computer. He was doing it on an IBM, working for IBM at the time, and having to print out on a dot matrix, probably even pre-dot matrix printer. So you can kind of shortcut that. So let me show you what it looks like. Always start at 0, and then use the constant. And if you do that, all you see is sometimes it's stable like this, and sometimes it's quickly stable. Now this one, this one. What they call these are the orbits. For every constant I pick, which you mentioned I picked about half a that's the orbit. But then the other constant I pick, anyone in school, and some of them are 4, and some of them are not. And some of them are not. The idea that maybe some points are special and some are not. What he saw, the technicians got it and they were like, well, he's got it wrong again. And they cleaned up his image and took all this dust that they assumed was printed. So like, this smudgy bit here, clearly not going to do that, we're just like to chop that off. And you don't have to stop cleaning them. I think what I'm trying to see is a weird mess of dust. So So it's even stable in this region. It goes into like 2 piles, but if I go outside the region, it disappears. If I go up here, you get into 3 piles. And in fact, Holly's done a lovely video on how many piles you start making, depending on which of these little bowls you go into. But the first time the Mandelbrot saw this, he had no idea about any of that structure. He just saw a shape, which shocked him. First of all, it's beautiful. It's kind of weird. But getting a viewer to display it, like I've got on the screen right now, you can go and watch any number of YouTube videos and zoom in on it. And you can see what Mandelbrot couldn't see. But he saw this little blob and thought, I wonder what that is, and he had no idea until he wrote his code better that it was another version, not quite the same. And you can just zoom in forever. And now, I don't think YouTube needs more videos of me zooming in on the Mandelbrot set. However, I'm going to do it anyway.
Ben, why are there different colours? Like, it's not always black and blue.
Absolutely. So the original Mandelbrot set that Mandelbrot saw was 2 colours. Stable, unstable, black, white, or whatever. I did black and blue. The colours you're seeing in this are an arbitrary decision, but they're not as arbitrary as you might think. So let's go back to the original, which is out here. Black for stable, but the colours indicate that it's unstable, but the colour indicates how unstable. And so if you think back to the very first question I asked you, I said, square it, square it, square it. And within 2 iterations, you're like, no, because it's big. And that's an indication that you don't need to ask any more iterations to know what it's going to do. With complex numbers, it's less obvious what it's going to do. It's much harder to predict, but eventually we proved, mathematicians, I say we, not me, mathematicians proved that if you go outside a circle radius 2, it's no good. But if you're inside, you can't guarantee it. It might be bouncing around near the edge, and it might stabilize again. And you see some of the orbits are complicated. So all you do with the computer is you ask it to check, let's say, 200 times. And if you're still inside radius 2 circle of 200, you're like, let's color it black. It's probably stable. But after like 50 iterations, if you've just crossed outside, you think, oh, now I know it's gone. But maybe the next time you check, it takes 60 iterations. And you're like, well, that's less unstable. Maybe I could color that differently. That was a long way of saying the different colors on the image are the different levels of instability. Really, it's how many times you check before you use it. And what matters when you zoom in is that the colors change really, really quickly. So all the colors on the screen here are indicating that a tiny movement of the original point gives you massively different behavior. And that's become what we call the sort of hallmark of chaos theory now, is where a tiny change gives you fundamentally different behavior. On the Mandelbrot set, you change every point you make is dependent on which C you pick. But Julia set, you fix one. And I can turn this software into Julia set mode. I'll do it slightly first. If I press J on here, there's the circle, which is the original Julia set. And that's in the middle here. But if I move the mouse around, you can see the Julia sets with different values of C start changing beautifully. Like, I mean, it's just a quick, sketchy animation, but it's already much more nice than the outlines you saw earlier. And what I love about this is the Mandelbrot set is kind of like a map of Julia sets. So if you go and find a bit of the Mandelbrot set down here, this is called Seahorse Valley, because it kind of looks like you've got loads of seahorses spiraling around. But if I switch to a Julia set around this point, it looks the same. But if I zoom out of the Julia set, you don't degenerate into Mandelbrot, you just get the Seahorse Julia set. There it is, that's as big as you get. So if you zoom in on the Mandelbrot set, you get little sort of like regions which are like the Julia set from that area. It's like a map. It's a geography of iterative stability. When you say it like that, it sounds complicated, but you just do something again and again and find out what happens in the long term. And the fact that it makes something so beautiful, I mean, it's become so cliche for mathematicians to get excited about, but I still get excited about it because it's lovely.
So, in the universe, there appears to be a pattern where shapes are repeating patterns that repeat at different sizes and angles, but always remain proportionally constant to each other. The multidimensional universe works in the same way, that is, constantly repeating patterns where proportionality is maintained but creating an illusion of size. For instance, the same geometries that is seen in our hologram is also repeated in our physiology, from our cells right down to the quantum level. The stars we see out there are also within us. Let's look at a Mandelbrot set and see what it does. Here we zoom it in, and this is what happens when you zoom in. Do you see the repeating patterns? I'm going to stop the video now, but keep watching for a few seconds once the video is stopped. Can you see all the repeating patterns that remain proportionally the same to each other, that form this beautiful design? And that's pretty much how the multidimensional universe looks like. Repeating patterns that are proportionally the same, but with different sizes. The strange phenomena of fractals is the technology used to control the hologram here, that is, repeating patterns of negative behavior that keeps mankind phase-locked into repeating history over and over again. And until mankind decides to move to another timeline, and that is what we will be covering in the next part of this course, you will understand this better once you have completed the course. The information I present is holistic in nature, with many parts forming the whole, so each part must be understood to understand the whole. And I hope you've enjoyed this introduction to the multidimensional universe. And you'll be receiving a copy of my book, The Multidimensional Universe, when you receive this video. So yeah, thank you for watching. See you on the next part.